Welcome to this lecture or talk, and please feel free to interrupt me during the talk. We can make it more informal and also interactive, right? Okay. I'll be speaking about explainability in graph machine learning, showing you some of the challenges, some of the solutions, and open questions. Work? Yeah. So graphs are everywhere. I assume that everybody here loves graphs. You can see graphs in biological networks, for example, in protein interaction networks, where the two nodes are proteins, and they are joined together due to the interactions that happen between these proteins. It could be financial network in which nodes are financial institutions and edges are transactions. It could be social network representing users and friendships or social connections. So graph machine learning is making highlights everywhere. It has been used to in various application areas like discovering new antibiotics. It has also shown high performance in making better recommendations and even assisted particle physicists in their tasks. So when we talk about tasks, what are these tasks that we can solve using graph machine learning? This is a non-exhaustive list of tasks that you can do on graphs. Some examples are node classification. For example, you are given a graph and some of the nodes, or let's say this is a social network in which nodes are users and edges are the social connections. And some of the users, the interests are listed, right? So these users they play soccer, they like these and these kind of movies. And for other users, you are interested in predicting their interests. For example, you can, using that information, you are able to recommend something to them. You might want to predict links between these users. You might want to refer them to new friends, so that's a link prediction task. Or you might want to classify the whole graph, classifying the whole molecule, whether it's toxic or not, which turns out to be a graph classification task. And then you might want to detect communities, coherent substructures in these graphs. But before we could do graph machine learning, we could do machine learning on graphs. The key problem is that graph is a discrete structure of nodes and edges, and our machine learning algorithms like continuous representations, right? So for example, if you have an image, you give this pixel representation as an input to a machine learning model. Or if you have some tabular data, you have this list of feature attributes which you can give as input to your machine learning data. But what do we do for graphs, right? So graphs have these, we have to give all this information about the node features, nodes, and the connections. So the first key step to do graph machine learning is to convert this graph into representations, right? So we need to learn first how to represent this graph and its elements, which can be then given to a machine learning model for subsequent training and predictions. One of the methods to learn this representation is this shallow node embedding based methods, in which the key idea is to find a representation of nodes in a graph, usually in an equilibrium space, such that you preserve some kind of similarity between these nodes, right? For example, if these nodes are considered similar in this graph, and the similarity can be defined in a number of ways, then these nodes should be embedded closer in this space. So we learn, so in these kind of methods, in these network embedding methods, you learn a lookup table, right? So for each node, you map it to a representation, and these are nothing but vectors of continuous numbers. Another way to learn representations is using graph neural networks. So what do they do? For the focus of this talk, we are only considering message passing graph neural networks, which work as follows. At each layer of this neural network, for each node, you construct a representation which is a function of its own representation at that point of time and the representation of its neighbors. And this function could be something, right? So it could be anything. It could be a mean operation, it could be a product, or it could be a concatenation. So this is some function. So at each year, you learn a new representation, or you obtain a new representation of this node, which is nothing but a function of its own representation and its neighbors, and its one-hop neighbors.
And by presentation, you still need a vector for those.
Exactly, still the vector. And you can assume that you have some initial feature vectors to start with. Okay. And you keep on doing this year by year, right? So, and these years are, in between these 2 years, you have a non-linearity. In the end, you learn some representation on these nodes. You can train this network. You can put another classification module here, and you can train this network in an end-to-end manner using the task objective. Okay. So one thing to note in case of GNNs is that if we are only talking about message passing graph neural networks, which takes into account the representations of their one-hop neighbors, then we can say that during the inference phase, to learn the representation of this node, if we are talking about two-layer graph neural network, as input, we only need two-hop neighborhood of this node. Because in the first layer, you are learning, you learn a new representation based on this one-hop neighbor. You do the same thing in the second layer, but till this time, the representation of these nodes were also updated based on their neighbors. So effectively, if you are interested in making prediction on this node, then you need its two-hop neighborhood at inference time. Right? And this is something we'll call a computational graph. So in case of graph classification, then you need the whole graph, right? So that would be the computational graph. Okay. So as we have seen till now, we learned some representations based on neighborhoods, based on similarities that we define, but then we end up with some continuous representation vectors, right? So what are these vectors? So there is these learning methods are completely black box, and you do not really understand what these representations encode. Or in case of supervised GNNs, when we are talking about these graph neural networks being optimized or being trained using a task-based objective, we are interested in knowing, well, if you predicted something for this node here, Bob here, if you, let's say, this is a financial network or this is a social network, and you declined loan of Bob applied for student loan and you declined it, you would like to understand why did you make a certain decision for this? Right? Or in case of node embedding methods, where you take input as the input as a graph, and then you learn some vector representations of nodes, we would like to know what do these node embeddings encode. I mean, in the last slide, we still, I mean, our question was much more clearer. We said, why did you make this prediction on a particular node, edge, or a graph? But here, what we are asking is a very vague question: is what do these node embeddings encode? Right. So in this case, what should even this explanation look like? Okay. Before I get into details of explainability, I would also briefly go through this terminology. We have post-hoc explanations and self-explaining models. In post-hoc explanations, we are interested in explaining an already existing model, right? So an already trained model. You trained the model, and now you are making inferences using this model. You are interested in knowing why this model made a particular decision in a post-hoc manner. In self-explaining models, these are usually inherently interpretable models or models which also output explanations while making predictions. Yeah, that's why I use the a bit more general term as self-explaining models. Usually, in post-hoc explanations, you would need to prove that your explanations are actually faithful to the model, right? So explanations should also follow the model decision logic. So there is an extra step where you have to make sure that these explanations are actually reflecting what exactly the model is doing. And in self-explaining models, usually we consider that these explanations are by design faithful to the model, and there is always a trade-off because you are trying to increase the interpretability. There might be a setback to the performance, whereas you do not affect the performance in case of post-hoc when finding post-hoc explanations. Okay. Another terminology, we might distinguish between local and global explanations. In local explanations, we are interested in explaining a prediction at an instance. And in global explanation, we are interested in explaining the complete model behavior. Right? So if your model is complex, making distinction between these two classes, you are trying to explain this model as a whole, but for instance-wise explanations, you can zoom in and say, why was this particular instance labeled blue and not orange? So what are the problems for these post-hoc explanations? In this talk, we are only focusing on post-hoc explanations. And what are the key challenges for these explanations? The first challenge is how to define explanations. What should my explanation look like? What is the objective of the explanation? Some guiding factors here are, with this explanation, we want to uncover the effect of the input elements on the decision making. We would also like that when the explanation is presented to the user should be able to understand the explanation. Okay. We will see that this kind of guiding factors do not lead us to a unique explanation, but multiple explanation styles which are being today used or proposed in the literature. The other tricky part is how to evaluate explainer and explanations. Usually, in literature, you will see that this evaluation of the explainer and the explanations is usually mixed up. Right? The first step in post-hoc explanations is that you need to validate your explainer is correct. Your explainer is giving you an explanation which the model actually used for making the decision. And this is a very difficult task because you do not have any ground truth. By ground truth, I do not know what exactly the model used. So you cannot really compare as you would compare other predictions. And when we are talking about evaluating the explanation, then we are saying, is this explanation useful? And you can give as an explanation some bunch of numbers which the model actually used, but can we as users use that explanation? Is it providing us enough insight? Right? So there are two steps in the evaluation of post-hoc explanations, which are usually mixed up in literature, and people mostly like to evaluate the explanation and forget to evaluate the explainer itself. They say, well, these explanations look good, they match human logic, this explainer is good. But the problem there is, the explanation could match human logic, but might not be the ones which the model actually used to make the decision. Okay, so we will be discussing some solutions to some of these challenges, to both of these challenges, but you will see that there are more open questions than okay. So in this part of the talk, we will be discussing one of the solutions that we propose for postdoc explanations for supervised GNNs. And no, sorry, that was too early. Let me also give you the kind of explanations that exist for postdoc explainability in GraphML. The first type of explanations are substructure and feature importances. As explanation, you could say that a prediction on verb was made. What influenced this prediction? These two neighbors are the culprits. These are the ones who influenced this prediction. If verb were not friends to these people, or if there was no connection, if these connections did not exist, then the prediction might not have happened. And the most important features. For example, Bob's loan was declined because of his old age or low salary. And this explanation in literature are usually presented as importance masks. And this importance mask could be hard or soft masks, which means either you say this node influence, or you could say this node has importance factor of 0.9, this one 0.1, this is 0, this is 0.3, and so on. Right. So you are giving some importance values. This could be 0 or 1 or some continuous vectors. Okay. And the counterpart to understand well what these explanations are, to counterpart in images or text are highlighting important parts of the input. Like for this dog image, highlighting the face and the body of the dog, that this caused the prediction. Or for this text, why was this text predicted with a positive sentiment because of these words like good, very good, and so on. Yes, please.
So is the mask predefined, or you can learn this mask?
Yes, so we have to learn this mask. So I'll go to a solution also, but here there is what's the form of the explanation. And you can see that it becomes much more complex in graphs, where you do not have to only talk about the properties of the node itself, but also of its neighborhood. Because the input is more complex. And the methods which are used for images or text cannot be trivially adapted for graphs, because you also have to look at the interplay of features and the structure in the explanation. So you cannot just apply this method independently on the features and on the structure to get structure and feature explanations, but you also have to look at the interplay of structure and the features while the model is making a decision. Another type of explanations in GNNs or in graph neural networks are counterfactuals. Example, so this is the graph structure, this is the graph structure corresponding to some molecule for a medicine, and this molecule was predicted not being able to combat HIV. And then the explanation you would want here is, what could I do to this molecule so as to change the prediction to a favorable prediction? Okay. So these kind of explanations, which gives you a possibility for an algorithmic recourse, are called counterfactuals. Yes.
What's the difference with the example you showed before, where you are highlighting the nodes that were important?
So here you are looking for substructures or subpart or subset of the input which are mostly correlated with the prediction, which leads to a prediction. Here, and in counterfactuals, you are looking for substructures which leads to a change in prediction. Okay, that's the difference. counterfactuals are easy to understand with this example, in which I say Bob's loan was denied. Let's say you have a tabular data and Megha's loan was denied. Then I want a recourse, I want a possibility recourse. Give me a counterfactual saying that if your salary, you find a counterfactual closest to me, so all my properties are very similar to Elvin except our salaries. I say, if your salary was as high as Elvin's, then your loan could have been passed. Yeah. So basically, in counterfactual, you are looking for a smallest perturbation in the input graph, which could lead to a change in prediction. And the main goal here is you are getting an unfavorable prediction and you want your prediction to change to something favorable. Yes.
Obviously, people understand what tax also.
Yes, people also, there you would want to change the graph so as to change the prediction to an unfavorable one. You want to destroy the model learning. Here you want to give a recourse to the user, right? So these are also called actionable explanations, so that you can do some action on these explanations. Okay. Yes.
Another question. Okay, different objectives. So when you have chosen a learning model, is that desirable such that the model is robust to small perturbations?
Yes.
So basically, it doesn't work from design system what you want.
Yes.
If you are robust, then you will not find this solution.
Maybe you need a very big change.
Yes.
Not small perturbation.
Not a small perturbation, but that's an interesting viewpoint, right? So I have to also check on literature, what do people say about these things, right? So because in principle, you would want your model to be robust and still be able to compute counterfactuals. Yes, please.
So this counterfactual space can be almost infinite, right? It's like
Yes, yes, exactly.
How do I know what is what?
Usually what people do is use heuristics to find these counterfactuals. So they have one graph, they go to small changes and look at the neighborhood. If there is a change in prediction with this instance or not. So you start with this graph and you start making changes, right? So you drop an edge, you add an edge, you add a node, and you limit the space of your search to something manageable using some heuristics. But you're right, this space is infinite. But also you are interested in small changes, because if I go back to this loan example, if you say you have to change your salary, you have to change your house location, you have to change your country to get this loan accepted, then this explanation is also not useful for you as a recourse. Does that answer your question?
Mm-hmm.
Yeah. In graphs, in the current literature, people are looking at this counterfactuals only from the point of view of graph structure, but they have not really touched it from the point of view of features, right? So in graphs, you also have node features, edge features, and structure, but they present counterfactual explanations only in terms of structure, meaning only in terms of changing the structure of it. Okay, then very recently, a few papers have come up, which says we will present explanations as concepts which can be understood by humans better. Right? In graphs, these concepts could be some substructures in a graph which people can understand, maybe a community structure, or some things about which is easy to assimilate and understand, because this node, this graph was classified with something because this has some house structure in it, or it has a node with the degree greater than 6. Again, to understand these explanations are still not, these are at a very at an infancy level, this concept-based explainability in graph neural networks. But to appreciate how concepts can help you, I'll show you an example for images. So here, this this room was classified as a bedroom because of these concepts, right? So because it has a wall, it has a floor, it has a carpet, it has a lamp, it has a bed, it has a cushion, so on. But these trying to even find these explanations in graphs is very difficult. And at the moment, there have been some papers which only look at toy data sets, for example, the synthetic data sets. Why is this grid graph, right? So why is it classified as grid? Then you can output certain substructure of this graph as an explanation, which you can see as a concept. Okay. As you can see, in all these explanation methods, the first one focuses on the substructure and feature explanation, focuses also on the interplay of substructure and features, right? So they consider substructure and features together, whereas the rest of the explanations usually focus only on the structure. So I'll try to give you a solution, or one of our proposed solutions, sorry for the bias, for finding substructure and feature explanations. And doing that, I'll also touch upon the nuances of defining and finding such explanations. Okay, we already agreed that we can define explanation as the effect of the input on the decision. So we define explanation as a subset of the input which leads to the same prediction as the whole input, right? But the problem here is the whole input is also a valid explanation. If I use the whole input, then it would lead to the same prediction, right? Then a natural thing to say is I want a small subset. So I need a sparse explanation. The problem then is, you say, if you use only this part of the input as an input to your originally trained graph neural network, your predictions should stay the same. What happens to the not selected part of the input? You can say, I'll put everything to 0, but 0 could also have some meaning. What if you put everything to 0 and the other user put everything to 1? The prediction might change. In principle, what I'm trying to say is that there could be a dependence on the explanation that you found and how you set the variables which are not part of the explanation. But they should be independent, right? So whatever you set in the not selected part of the input, your explanation should stay the same. And with that concept, we define stability. We say the part which is not selected, set it to some random values. Not really random, but using the empirical distribution of your whole input so that you stay within the distribution of your training data. And then check. So you do it multiple times and then check if in expectation, your prediction stays the same. So as an example, if you are looking at this graph and you make this prediction from this orange node here, you predict some of the most important nodes and features as an explanation. You can construct this node feature mask in which green, so all these green nodes are the selected one, the green features are the selected one. For the nodes which are selected and their features which are selected, you set them to the true values and put random noise to rest of the values. You keep the input intact. You do not throw away any part of the input, but you just replace it by random values, so as to improvise the situation that whatever else was the input, the model just looked at this explanation to make the decision. Yeah, this idea of this comes from the theory of rate distortion theory, and so you can create your perturbed input and try to find an explanation such that with this perturbed input in expectation, your prediction stays the same.
Like when you do these random perturbations or a replacement, you just do it once, or do you do it like
you do it multiple times to compute the empirical expectation.
Is this also as a way to measure the robustness to input perturbation somehow to non-relevant features?
Yes, to non-relevant features, but it becomes a different story when we're talking about small changes in input. So in input perturbation, it's like small changes into input should not be in the explanation. I'm not sure about if that works here also, because small changes in graphs could really mean a large change.
It's assuming you have many input features, then we want to select the cell in the tree. But it's possible that you have several possible combinations.
Exactly.
In the computational field.
Very good point. Yes, this is the NP-hard problem. This is subset selection. You do this heuristically. It's computationally very heavy. All the machine learning for graphs data course know that. They complained about that. Yes, I mean, one can also think of approximations to the. I mean, we already have an approximation which is also very slow. One needs to improve that. Computationally, that's a problem. But the other point that you raised was even better, very nice, is that multiple combinations are possible. Yes, we found out that multiple explanations are possible. The model used multiple explanations, could have in its own mind multiple design logics to reach to the same prediction. That even makes the things even worse, because then you do not know which explanation to present. But I mean, in all of these methods, right? So this is the issue, right? So you cannot go through all the subsets when the feature dimensions are high. I mean, we use a greedy approach to find this, which increases the complexity of the algorithm, but one can also do some tricks with using gradient-based estimation, which will give you inferior explanations, but at a higher speed. Thank you. Okay, so I'll quickly go through the second challenge of evaluation, right? So I've already touched upon certain parts, certain problems in evaluating these post-hoc explanations. I would divide this evaluation of post-hoc explanations into two parts. In the first part, we are only focusing on evaluating the explainer. In the second part, we are evaluating the explanation itself. In the explainer, we would like to know that if actually the explanation makes sense, if your explainer is correct. And in the second part, we could check if the explanation matches the human logic, if it is useful, or even to evaluate the model, if the model is using the right logic. Okay. So first, we are interested in checking the faithfulness of the explanation, right? So which means whether the explainer is giving you an explanation which the model actually used. One way to do this, in literature, it's done like this. So you can keep only the most important part of your input, keep the explanation and remove everything else, and check if that's sufficient to reach to the same prediction. And on the contrary, remove your explanation and check if with the rest of the input, the original prediction changes. This has a problem with sufficiency. On comprehensiveness, if you remove, sometimes the inputs could not be removed. For example, you cannot just remove the features. You can remove the nodes and edges, but you cannot remove the features. And removing nodes and edges also could make your explanation subgraph disconnected. Yeah. And what does it mean in case of message passing networks? If you have isolated nodes and isolated edges, they are actually not contributing to the message passing of the graph neural network. One of the solutions to this could be using our RDT fidelity measure, in which we do not actually remove the not selected part of the input, but randomize. The next part is complete input is also faithful, right? So we should also check for if the explanation is not trivial explanation, it's not the complete input itself. In some cases, yes, it could be the case, but in most of the cases, we are interested in finding sparse importance masks. So in case of hard mask, when you have 1-0 explanation, it's easy to compute the sparsity. But in case of soft marks, when you have continuous numbers as importances, it could happen that this is a real example from a real paper. One of the methods here and explainer, we looked at mask values, important mask values that came out of for some of the data sets, and we found out that these mask values are very uniform. So all of the features have almost equal importances. Such an explanation is also useless. In this case, you can check the entropy of the distribution of this mass to say lower the entropy, better it is. Okay. The other metric, which somehow comes in between of checking the faithfulness and evaluating the explainer and evaluating the explanation, is that you do not really have ground truth explanation. You do not know what the model used. But what you can do is, like Alvin suggested in adversarial attacks, what we do is you could incorporate certain correlations in your data, which you feel or which you think could change the prediction of the model. You train the model again with this new correlations. If the prediction of the model changes, then it means that this model have used some of these correlations. And see if your explainer can uncover those. Right? But in principle, it's very difficult to use this metric in the sense that choosing these correlations, how to insert these correlations is very tricky in the first place. There is no principled way to find this. The next part of the explanation, I mean, once you are satisfied if your model, if your explainer is giving you an explanation which actually matches the model logic, then you can start looking into the utility of the explanation, meaning if it's useful for us or not. If this explanation is also telling you something. For example, we just constructed a graph data set out of this text data set, and we let this text data set annotated by users, saying that why is this text part assigned a negative sentiment, why was it positive, which words influenced you, and then you could check the explanation which was given by your model or by your explainer. Does this match human logic? You can just compare the explanation which was generated by your explainer and the explanation provided by a human, which gives you a sense if it's useful, if it's going in the useful direction or not. Yeah, but be careful. First, check the faithfulness of your model. Your explanation could be very nice, could be what you are looking for, but it might not be the one which the model used. Some of the evaluation schemes which have been used in literature, which have big problems, is people have planted some subgraphs in the model, and they said your explainer should be using that, right? So they said, so this subgraph was planted here, and your explainer should detect the subgraph because the subgraph is the reason why this graph was classified into a particular class. But how do we know if the model actually used this? Model could have arrived at the right decision because of something else. People have also, what they have done is that they have trained a number of GNN models, and they said if they reach the same performance, then they should be using the same explanations. So if you train this GNN 1, 2, 3, they have 99% of accuracy. They let the explainer run on these models. They expect the explanations to match. Again, you do not know. These models could have arrived at right decisions, but using different logics. Okay. I do not have much time. I'll just 2 slides more. I'll not go into details. We have some work also on explaining node embeddings. Here the problem is much more difficult than when we are talking about explaining supervised GNNs, because here we do not know what do we want to explain. So given a graph with all these representations, let's say Euclidean space, what we did here is to match to map the dimensions of these node embeddings. So the dimensions are themselves uninterpretable. You do not know what they encode, right? So you have these feature values, but you do not know what this dimension corresponds to. What we try to do is to match this dimension to a substructure in the input graph. Which means that this dimension, you can interpret in a way that this dimension is contributing maximum to prediction of edges in this substructure. Okay. Let me skip this slide because of the time and finish it in this slide. Explanations. There is more work that we are doing on explanations, not only in finding explanations, but also the interplay of explanations with privacy. Can these explanations reveal sensitive information about your training data? Yeah, there is one part if these explanations are useful or not. They might not be useful, but are they revealing something important that you want to hide in your training data? I'll not go into the details, but please look into these works if you are interested. Last but not the least, join us in the PEST course of Masters Machine Learning for Graph Data. There are already some students who could say very good things about the course, I hope. And I'm also organizing a workshop on the interplay of explainability and privacy in AI. If this topic intrigues you, please join us on 8th and 9th February. You can click on this and find the webpage. Thank you very much. Yeah, so